function approximation Bechamel plus function approximation. We're going to spend this week on this topic. And the question here is whether in the ideal case, when it seems that like you do have, okay, so if you want to learn this, okay, function approximation, just linear features, so linear prediction. And so the ideal case from the perspective of regression is when the design matrix has a very nice structure, right? Like the minimum eigenvalue is the best possible. Then from a regression perspective, you are exploring all directions in the feature space equally well. And you can learn pretty quickly a regression function. And so that raises our hope that, okay, like maybe the hardness only comes when these design matrices underlying the features are not that nice. And so maybe when they are this nice, we just need to make sure that we have coverage in the feature space, so to say, right? Like, that is the question. So specializing to linear function approximation, question is coverage in the feature space enough for regression? So this is like optimal design. So someone gives you, like the G-optimal design distribution. Then we have seen back in the day that all the errors are very well controlled if you only consider regression problems, right? But we do have reinforcement learning problems. There's a planning component. You only have these small snippets, these transition quadruples. You might not have full trajectories, and even if you have full trajectories, the trajectories might not have a good coverage everywhere in the state space. They may give you this, like the optimal design, and the question is this sufficient in a reinforcement learning setting to be able to come up with good policies or to avoid a given policy in the bad setting? Right? It's a reasonable question. So we know the answer to this when we have special features, tabular case. So, in that case, the feature mapping states and actions to this space, and just using the indicators for every state action pair, you have an indicator component of the feature map. Good design, that means that you're sampling the states and actions from some distribution mu. It is a distribution over state action space. And the good design would be such that this design matrix has a minimum eigenvalue of the size of 1 over d. So here, this is Rd. So in the tabular case, d equals s times a, right? And so that's just the uniform distribution. That's just describing the uniform distribution in a complicated way. So in a tabular case, It's going to be satisfied if your sampling distribution is a uniform distribution. We have spent quite a bit of time understanding that in the tabular case, when you're uniformly sampling state action pairs, then you can efficiently solve the off-policy estimation problem, off-policy optimization problem, everything can be done efficiently. Polynomially in the number of state action pairs. Which is polynomial in D as well, because D is the number of state action pairs in this case. So we may have high hopes that this is going to work. Turns out, it just doesn't. This is not good enough. So it's like this story with batch area is like walking in a minefield, right? Like, boom, and then the mine explodes. Like, this didn't work. This is not going to work. Yes?
What does FAPP stand for?
Function approximation? It's, oh, yeah.
Oh.
That's a good point.
So
I use that abbreviation since my PhD years, so, but I never taught anyone. I guess no one really asked, like, what's that?
So
Yeah.
just FA.
Yeah, but like FA is too on this thing, so just add the PP. Okay. All right. Okay. So what are these results? So let's start with a paper by, what is this? Wang. Poster. Kakadi. 2020 paper. And it's asking exactly this question. This paper is mostly concerned with off-policy evaluation, OP. As opposed to OPE. I guess some people would say OPE. But okay, so maybe OPE should be like when the optimal value needs to be estimated. So that's estimating V star, maybe at S0.
What does T stand for?
And this is like estimating V pi of S0. Huh?
What does T stand for?
T?
Optimal evaluation?
Optimal. Yeah, it's like, just
Sorry.
very that.
Okay.
If you have any better ideas, let me know.
No, I was just curious if that's because OP is off-policy evaluation, but this is optimal evaluation?
It's like getting the optimal value,
Okay.
estimating the optimal value, as opposed to getting a policy. So what is pi star?
Okay.
So that's off-policy optimization. And then like, okay, it's all off because it's batch. It's all very confusing. It's offline also, but it's really batch. But people are calling these things in these names. All right. So this paper is really about this, but there is some relationship between these problems that we should talk about a little bit later.
I was going to ask, is one easier than the other? Is there not like a result that's a
That is the relationship,
Yeah.
right? Like, what are you guessing?
My guess is if you can't do OPPE, can you hope to do OPTE?
Yeah, so one thing that you can't, and then if you can't do OPT, then you can't do OPO. Right?
Who needs words? to
And-
agree?
Okay, so maybe the reverse questions are a little bit more interesting.
Oh, like if you can do one, can you do the others?
Yeah, like, if you can't do OPO, does that mean that you can't do OPT? Maybe. But well, one has to think about that. Probably, yeah. It's should be true. It should be true that these are pretty much all the same in terms of difficulty.
Isn't technically one problem have a larger solution space than the other problem? Like there's only one V star, but there are multiple pi stars.
Yeah, I mean,
Oh,
that's fine. That on its own shouldn't bother us. And here maybe it's like, it's really a question of like how to act at a state as not. Maybe that's like the local version of this is what is a better correspondence to the rest. And then you can try to guess that, I mean, if you want to show that if you can't do opt-O, then you can't do opt-E, then somehow you have to encode the value that would need to be estimated in terms of like, would you choose this action, would you choose that action? If you can answer those questions, then maybe you can bracket the value, and then you keep bracketing, and then like, okay, so maybe there is a log 1 over epsilon reduction or something like that. That there is an extra blow up of the number of samples needed of log 1 over epsilon at most. If you could do OPO, then at the price of like log 1 over epsilon times as many samples that you need for this, you can also get a value or up to epsilon accuracy or something like that. Right? Homework? Next year? I don't know, something like that.
Wait, so in the opt-E, if that one has a negative result, then OPPE definitely has a negative result?
Well, that's kind of the similar question, right?
But isn't opt-E just evaluating one policy? And then
You don't
for
know
any
which.
policy?
It's like, yeah, that's kind of the difficulty that.
But there could be any, like any of the optimal policies could be an opt-E?
Yeah, but like you don't even know which policy you're evaluating.
Yeah.
So it's like a
Yeah.
slightly different
Right.
problem. So it's like you have to think about, okay, again, how to encode in terms of optimal values the value of a policy.
Mm-hmm.
So you start with an MDP, the value of the policy, and then you somehow introduce a new MDP such that if you knew the optimal value in the new MDP at maybe a new state, then you would know the value of that policy. Okay, so it shouldn't be that hard to do this, right?
also, I guess I guess like their outputs, like the maps are mapped to different ranges. Like one's over the actions, the other one is over the reals.
Sure, but like
Yeah.
it doesn't matter, right? Like because we are comparing them in terms of how many samples they need
Yeah.
to get up to a certain accuracy. And so here we have two parameters, by the way, for all of these problems, the epsilon and the data. So epsilon is epsilon suboptimality in terms of either estimating the value, like your epsilon close, or the optimal policy is like your epsilon close to the optimal policy in terms of the action that you chose and so forth. This is just like a confidence parameter, so with probability 1 minus data, you should be able to do this.
Yeah, my question was like, what is exactly means that we have this G-optimal design in the batch case, like we have a G-optimal data set for each batch? And the second question is like, even in the previous case when we considered that we had a G-optimal design core set, we kind of did it like off policy because we had a policy and we did rollout and we get a batch of data.
No, because like we got the rollout from the policy. It was on policy. It was more like on
Yeah, but
policy.
during the rollout we didn't change the policy. So basically we
Yeah, but like it was not like that. You would roll out with some distribution over the actions such that it doesn't matter like what policy you want to evaluate. You can evaluate every policy. No, like it was specific to the policy,
So
right?
Yeah, I guess here, right, we're rolling out with a policy that's not the policy we're trying to evaluate.
Yeah, that's the problem.
okay. So basically then it means that that policy that we don't want to evaluate is rolling out from the same core set like which is G-optimal
Yeah.
design.
Or maybe it is just generating IID samples from this distribution new SA, and then the next state, and the corresponding reward. This is your data. And you just keep doing this. You don't even have trajectory, so that's like another setting, this Z design setting. or you could be choosing a logging policy such that the logging policies induce distribution over the state action pairs satisfies this, which is basically saying it's close to G optima. This could be polynomial in D, and then we would still be fine, right? Like, if this is just a 1 over D squared, it's still fine. Just what it shouldn't happen is that this is like e to the minus D, then like, no, that's gonna be bad, because usually this minimum eigenvalue, the inverse of it, appears like very naturally when you want to evaluate anything and like do any calculation with least squares. Right. Okay, these are excellent questions. Yes.
So I am still confused the relationship between OPPE and OPTE.
Okay.
So in one sentence, like which one is like, can we use this one to get that?
In one sentence, it goes both ways.
Both ways. Okay.
Yeah.
They are like very similar problems.
They are very similar problems. Yet you can define these different problems. They are seemingly different, but you can argue that they are really the same.
Just like constructing MDP that we solve that MDP, and then in the original one, we get the value for the original one.
That's right. Like, it's like a reduction approach, right? Like you try to reduce one problem to the other. If you have a solution to the other problem, then using that solution, you try to solve the problem you had. So you do these constructions. And lo and behold, in all of these cases, like, yeah, you can travel between them. So one of the cases is okay, so I have to be a little bit more specific about things here. So it's like, so we have this epsilon and data, and so to be precise, in the OPPE problem, in all of these problems, you have your data, that's your input. The algorithm eats the data, and it has its input as epsilon and data. It has maybe access to a feature map, so it knows the full feature map if you are in this featureized setting. And then in this case, it would have as an input the policy itself, and of course S naught. And then it would be told, okay, give me the value of this policy with probability 1 minus data up to an additive accuracy of epsilon. That would be that problem. So here, since we're talking about V star, the reduction that says that this is at least as hard as this one says that, oh, you would need to, I mean, if you can do this for all the policies, then of course you can get the optimal value, right? Like if I need to solve, like for V star, a very simple approach would be enumerate all the policies, get their values, choose the max. Problem solved. If you have too many policies, this blows up the sample complexity. Well, the number of policies for which we need to do this, if we are not using any further structure, it's like all deterministic policies. So the number of those is, so the deterministic memberless policies, the number of those is going to be, I don't know, a to the power of s. And so since we are sharing data, we need to use a union bound. The log of the number of policies is what's going to appear in the sample complexity bonds. So the log of this is s times log a. So the sample size that we need to guarantee that our estimates are epsilon accurate for all these policies has to be blown up by this factor. compared to just evaluating one policy. So that's the union bound price. So if this is big, then we're dead. So when we are in this featurized setting, usually we do have two parameters, the dimension and the horizon. And we want everything to be polynomial in the dimension and the horizon. And here we see that in this simple reduction, the number of states appears, and the log number, okay, so the A is fine. Like, we already started to live with that, like, okay, we need to add A. And if you're polynomial in the number of actions, you're still good. Like, you're happy with that. So that's fine, and log A would be even better. Like, oh, awesome. Only logarithmic dependence on the number of actions. But this linear dependence on the number of states should give us a pause, whether this reduction works the way I said. It turns out that like, if you have hardness then, for this problem, that S is polynomial in D, then everything is polynomial in D. Right? So we just have, S has to be polynomial in D, H, and A. So if S is polynomial in D, H, and A, then the blow up of the sample complexity is just a polynomial. So the reduction still works. So from the point of view, whether the sample complexity stays polynomial, if it was polynomial for one of them, you have equivalence. So here, there is a caveat that S should be polynomial in the relevant quantities. I don't know. Maybe A and 1 over epsilon and log 1 over that. Those are the usual culprits.
So S can't be too big.
So S can't be too big if you want a reduction like that.
Oh, okay.
If you want to argue that if this problem is hard, then this problem is also hard, and you want to, the only argument on your behalf is just to avoid all the policies, then you run into this problem. So the number of states shouldn't be too big. So that's a question.
This is the case when function approximation isn't buying you much in compression. Like it's only buying you a polynomial compression.
Oh yeah. If S is polynomial, anyways, then it's not really buying you much.
Okay.
Right, like in terms of polynomial equivalence, it's not doing anything. It just messes up things. If you have hardness results, then what happens is that, yeah, we added function approximation that adds complexity. If we just stayed with the tabular case, we would be done. The only thing that would change is this requirement, right? So in the tabular case, this requirement means uniform distribution over the state action pairs, roughly uniform distribution over the state action pairs. In which case we know we're good. It doesn't matter whether you just have snippets or trajectories. If you have this uniformity with the state space, everything is beautiful. In the tabular case, that just works. So the real question is like, can the features really mess up things such that like, linear regression should work? You added these features, you're hoping that with this, you're kind of relaxing the uniformity assumption because you don't require uniform distribution over the full state action space, but you require only some uniform coverage of the feature space. But then the question is like, does this mess up things? And the answer is yes. All right. So this, the first result is this theorem that says that for every D and H, this dimension is horizon exist an MDP M, the feature map on it, such that, so this MDP looks like this. There are states and actions in it. There is a transition kernel, and it's homogeneous, and you can make it deterministic, and there are stochastic rewards, so it's like, okay, so we are running into this notational problem. So I will use Q, right? So that's the joint next state distribution over the next states and the rewards. So this is deterministic dynamics and stochastic rewards. We are in the undiscounted finite horizon setting. This is the MDP. The feature map is just doing the feature extraction into D dimensions, and as usual, nothing bad happening with the features being too big. The immediate rewards that you are deriving from here, the immediate expected rewards are in between 0 and 1, so nothing, no weirdness happening there. Okay, so this is the MDP, and there exists also, so this is just for M and phi, and there exists a distribution. Okay, so we have this layer structure for the state space. So the state space is going to be, like stage 1 state space, stage 2, stage H. You can only go forward. And so the distribution factorizes accordingly, but if you take, so this distribution is going to be such that that condition is going to hold. So there are 3 things that hold. So 1, so what are the features good for? They're good for representing the action value function of all the policies. So this lies in the span of the features. For all pi memoryless policies, deterministic or not. So that's like, okay, things are not going bad because we cannot represent the action value function. It's through compression. The features are doing what the strongest thing we may want them to do. Like, they're really, really good features. So our hopes are high because of this, and also because this minimum eigenvalue is actually the best possible. It's 1 over d. That assay is sampled at random from you. Maybe 1 over dh or something, because like you uniformly choose a level, and then you uniformly choose a state action pair at that level. Oh, I didn't tell you, but so going back here, the number of states is not large. So the number of states is going to be d times h of that order. And the number of actions is also not large. It's going to be 2 actions. It's not like that things are going bad because we have lots of actions, lots of states. No. Like, we are not even doing much compression. We are just Yeah. We're just trying to relax this the uniformity condition, exploiting that we have these strong features. And then the bad thing, for every A, batch, I don't know, OPPE. Algorithm. Which is epsilon delta sound. So an OPP algorithm is epsilon delta sound if whatever polycate is given, plus the data, plus epsilon and delta, and plus the features and whatnot, it can always return an estimate of the value of the polycate. Okay, so S, there is an S not here. It's going to be this thing. It can always return the value of the polycate at S naught up to an additive accuracy of epsilon with probably 1 minus that. Then it's a well constructed algorithm, call it sum. Okay. It's a little bit messed up. All right. So this is a family of MDPs, which is parameterized by some value R, and this value, okay, so let's call it theta. Okay, not multidimensional. Don't. Okay, kappa. And kappa appears in the rewards, and kappa is just a number between 0 and 1. So, for no matter how you choose this algorithm, there exists a value of kappa. Choose an adversary for this algorithm such that the number of samples required by A on M kappa, if it needs to return an epsilon delta accurate estimate, is at least d to the power of h. So in short, the sample complexity is exponential in the planning horizon, as long as the dimension is at least 2.
I guess we talked about it in the previous class, but what is the target for regression in this OPPE algorithm? Because when we don't have the access to like return, how we can like evaluate the value functions?
This is like this theorem just tells you it doesn't matter how you try to do it, it won't work.
Mm-hmm.
It's not going to constructively suggest anyways because none of them works.
Or that one is not.
That is the problem, right? Like there is no obvious target. Like if you try to make up some target, you end up doing bootstrapping. If you end up doing bootstrapping, the errors are going to compound. See my post in the ML theory thing. And it's exponential in the planning horizon. It's like all those errors are multiplying, and you're dead before you blink.
That one was not like a positive result, I guess, or it was a positive result.
Which one?
That one that paper that you mentioned.
No,
Uh-huh.
no. This is this page. This is this theorem.
Uh-huh.
In this field, there are no positive results except for the tabular case. And even those like a bit questionable, the positive ones. Yeah, I guess they are. So we should, I Did we talk about it? So Magdi has a paper. But of course the conditions are gonna be naturally somewhat stronger than here because these conditions are just not enough. So you have to have something more. So if you have linear MDP, for example, and reliability and whatnot, then I think you're good. So I think that's a paper by Magdi and students.
Maybe like the previous class, if you have like the trajectories instead of like disjoint like quadruples, it's working like it.
Could be. So let's see the second theorem. Yeah, it's a natural thought that could work. Okay. Just continue here. So the other theorem, but maybe before we do that theorem, let me just pause for a while and think about what's going on. So first of all, like seeing this theorem, like someone should be a little bit surprised, right? Because for the tabular case, everything was just fine. And now, it seemed that it was an innocent generalization of the tabular case, and now nothing is fine anymore. So it's not so innocent. So why a tabular algorithm cannot solve this problem? So what could be that construction that makes it so that the tabular algorithm cannot solve this problem? It has to be so that if you take the tabular features and this condition is not satisfied, because if it was satisfied for the tabular features, we would be fine. So somehow there is a discrepancy between these two feature sets. And this is what is being played here. So the construction by and large works this way. So here's a state space, state space. Horizon equals 1 and horizon equals h in the bottom. There are all these states. So here there is going to be like roughly d over 2 states for whatever reason, but like just think about that it's d. It's just a factor of 2. And there is a special set of states outside of this bunch, such that knowing the reward here along any of these transitions would reveal the identity of the MVP of those the kappa value would be known. If you know kappa, these MDPs only differ in kappa. They are not different in any other means. One real value that you need to know. So this kappa would be revealed if you make any transition here. But we're going to make it so that our conditions are satisfied and we're not making any transitions there. Therefore, kappa is not in the data in a direct way. So how do we do this? Well, we're going to assign features such that we're going to play uniform distribution here. And it's basically the tabular features here. And uniform distribution. And somehow we very carefully choose, so there will be actions that are going just down, and there are actions which are exiting from any stage to the next stage, and then they continue this way. So you can go down or you can quit. Here you can, it doesn't matter what you do. You go down or quit, you're just going down. And actually, this is going to be S0. And whatever policy you choose, so that's kind of the lie about this whole theorem. It holds for all policies, but all the policies just go down on this line. So the value of this state is independent of the policy. The policies can, like, go down and quit, go down, quit. These are the policies that, this is what the policies can do, deterministic dynamics. But the value at S0 is independent of what the policy does. Only depends on the value of kappa. You will need to know kappa. And everything is constructed in a careful manner such that with this, the feature coverage is satisfied here with this uniform distribution. So somehow the features here lie in the span of the combination of those other features. So it's like a nice mixture argument is holding. So that's kind of the neat part of the argument. And so therefore, learning about, like here, so at the end of the day, to make everything consistent, in the bottom, of course, you will need to have rewards, which are going to also depend on kappa, to make all these equations hold. But those rewards can be of very, very tiny scale. So the signal to noise ratio is going to be really bad. So the only way you can learn about the value of kappa from the data is by observing many, many times things here, because here the signal to noise ratio is pretty bad. And everything is set up in a nice and consistent fashion, and yet you can't learn the value of kappa. So what happens to the tabular like learning algorithm? Well, the tabular learning algorithm, like no algorithm is seeing these transitions, so it's like it doesn't matter whether you want to use the features or you don't want to use the features. It doesn't matter. The condition is insufficient to provide the tabular coverage. It can provide a feature space coverage, but the MDP is constructed in such a way that all these value functions lie in a lower dimensional space. And because of that, you can excite all the features in all the directions and not learn the values of the policies. So it's like that is the story. That the MDP structure allows you to somehow do this compression so that it seems that you're exciting the features, but you fail to learn the critical information. Okay? So that's the gist of the construction. Details are in the paper. That is a related construction which is much easier to understand. So maybe we should cover that now. That's for the setting. It's not as general as this one, but you could generalize it, I guess. It's just for the single dimensional case. So if you have one dimension, then this coverage condition, like, what the heck does it mean? It's like you choose that feature and then like, oh, you square its value, and that's, I mean, like, it doesn't mean much, right?
You just have a chain. You just observe this H.
Huh?
This H-dimensional chain, but any policy is optimal in the sense that.
What are you talking about?
Oh, you
Sorry,
said if we had
like
one.
you're still talking about this?
Yeah, you said we had one dimension.
Yeah. So we are moving away from this, but like it's just fixating on this condition here, and the feature dimension is 1 now. Then it's like there are no multiple directions to exceed. It's about the magnitude of the squared value of the feature. If it is e to the minus h or something like that, like then that would be bad. So the condition is going to say that it should be roughly constant or like polynomial in, I don't know, the inverse of h, something like that, right? So that you can make sure by choosing a constant feature or something.
Isn't there like, okay, say you have one dimension, but the 2 norm of that dimension is quite small. Isn't there like a transform you can do to make the magnitude a bit larger without losing any like without like blowing up approximation error?
Yeah, so you can upscale the features if you downscale the parameter vector. But upscaling the features, we put an end to that because we said that the 2 norm should be bounded by 1. So that's why it's kind of important, because otherwise you can trivially like make sure that this always holds by upscaling the features, right? You just like scale up the features, downscale the parameter vector. This always holds. Like this only makes sense if the feature vectors are normed, properly normed.
I guess if you have one dimension, then it's just the value of the feature.
It is just like the absolute value or the squared value. It's just like, I'm just pointing out that there are no directions, no linear algebra, no complexity.
Yeah.
It is something super simple. Like this condition just says that, well, the expected squared value of the feature shouldn't be diminishingly small. It could still be diminishingly small, and that would be maybe bad, because then, again, the signal to noise ratio could be bad because of that. But this is going to be for the discounted setting. So we use a discount factor. H is usually 1 over 1 minus gamma. So gamma is, I don't know, 1 minus 1 over h, right? And the construction is, rather than stating what the theorem says, it's easier to just remember the construction. So this is by what friends? Phil. This is not a real paper. This is just an archive, like
2 pages.
2 pages thing. Jiang and Shi, I think. So they saw this paper and they were like, yeah, okay, so we understand, maybe we can simplify things a little bit, at least for the discounted setting. So we will have an MDP where all transitions are deterministic. The reward here is 0. The reward here is, I don't know, theta, which is, I don't know, between minus 1 or 1 or something like that. And we're going to figure out the, so the distribution, the new distribution, is going to focus on the first state, and it's going to completely ignore the second. You kind of see what the problem is. If you ignore the second state in the distribution, then there is no way you can learn about the value of theta. If you don't know the value of the theta, how would you be able to tell the value of any of the policies? Well, okay, all the policies are weighted the same. How would you be able to tell the value at S naught? Right? So the reward, the crucial information is not there. This is kind of like this, right? Like these guys were never in the data. So here it had to be a little bit more complicated because it had to be consistent. So something in the bottom layer, the rewards are dependent on this kappa. But here it's like super clean so far. Nothing, I mean, like we didn't say what the feature vector is going to be. So we want linear realizability for the Q's and the V's and whatnot. So for this, it will be useful to calculate the Q functions and the actual value functions and the value functions. So there are no actions, so it's like they're all the same. Very convenient. So V of pi or V of star, what is it? Like it's easier here So here we know what the value is going to be. At S1, what is the value there?
Theta.
Huh?
Theta.
Theta, but we are discounting.
Gamma.
Huh?
H theta.
Okay, so H theta. And what's the value here?
Gamma H theta.
Okay. So you can guess theta is going to be the parameter vector that is not known. So we want to pull it out. And the feature vector, I don't know, do we want to, okay, so if we want the feature vector to be normed by 1, then we have to make the parameter vector to be h theta. So then the feature vector is just going to be gamma and 1, and that is being multiplied by h theta. So now the remaining question is, what is if you want, these are state features or state action features, there are no actions, so it's all the same. So nu concentrates in the first state. So what's the expected feature vector? So this is phi. So it's just going to be gamma squared, right? You're squaring gamma. You put a weight of 1 on that, it's gamma squared. How big is gamma squared in terms of h? Well, it's over there. The larger h is, the closer it is to 1. So it's even better conditioned if you have a large horizon problem. And you can have as much data as you want. You will never ever be able to estimate any values in this problem. So it's like infinite sample complexity. It's like just missing the key value. So even though there is discounting, the discounting doesn't make it finite horizon either. So that raises the question of like, okay, maybe this should also be infinite? And this was a loosey under lower bound? And the answer is no. You can get this as an upper bound. if you have this thing in mind. I'm like, okay, so how do you get it? It's like you just run LSP or whatnot, right?
Doesn't this algorithm, this setup right here, not have the coverage assumption?
It has everything. It has the coverage assumption.
Is coverage not coverage of?
It's the feature space coverage.
Yeah.
It's like this whole lecture is about the difference between state action space coverage and feature space coverage. So even when the features are very, very friendly and you have feature space coverage, it means nothing in the batch case. It was not the case in the online case when we could plan, when we could do stuff. These very super helpful features lead to polynomial sample complexity. Only in the batch case, things are completely ruined.
Is that true? I mean, like, say we have one layer neural network, and then we have nice bounded L-unit dimension. Maybe these are, is this the?
I mean, so this is a linear feature case, right? Like L-unit dimension is nice. It's just the, so everything is beautiful. So the setting where Q pi is in the span of the features, you can run least squares policy iteration. You get polynomial sample complexity for this. For the planning setting, for the online setting later on, you can learn that you would get still the same. So it's the batch setting. It's the culprit. It just, the batch setting is a bitch.
So this is kind of, I brought it up originally, but could you then study the batch setting where it's like how many, almost like a PAC-RL setting, like given the data you already have, how much exploration would you need to do to like improve your estimate by some factor. Like maybe in this problem, if you had like one exploration round, you could then estimate B star very accurately. So like the price here is
For any finite number of exploration rounds, you can extend these.
okay.
The number of exploration rounds should be scaling with the relevant quantities. And then we're in online setting.
Yeah.
So it's like, yeah.
But then I guess we move away from needing to guarantee. We can then have coverage in the feature space might actually be useful.
Yeah, in online setting, yes.
Yeah, like to the
That
point.
will be the
If you have coverage
question,
in the
right?
feature space, would you then have, instead of polynomial exploration, maybe you could get you only need maybe like some logarithmic exploration rounds to just, no.
That's too good to be true.
No, I'm just kind of curious, like in the batch setting, when does what's a batch setup that would make online exploration easier as well? Like to the point where it wouldn't just be I guess like theoretically you take the batch setting.
Warm
but-
start or?
Yeah, like when do warm starts actually like buy you something that isn't just restarting the algorithm from scratch?
Yeah, so you can write regret bonds a lot of times as a function of like how good was the initial data and so on and so forth. People do that. So you can make it in a way instance dependent.
Okay, where the instance isn't the problem, but like also like
The distribution over the data as
yeah.
well.
And the problem.
And the problem, yeah. That works. Okay. So the next theorem that I was already alluding to is because you might think that, okay, the problem is with the snippets, right? That you're in the setting and then you would need to somehow like just jump out there, and then if you jumped out there and you would continue that, then you would immediately see that things are good, right? Like you would immediately see the parameter vectors. That construction definitely doesn't work if you can generate trajectories from whatever policy, like take a uniform policy, it won't work. So, are we optimistic about this? Is it gonna work? Just no way, right? Like we have already learned the lesson. Like this Bachelor just never works. But okay, it's still worthwhile to ask the question: is it gonna work? How would you modify this example to show that even if you can emulate trajectories, then maybe the result should be that you can, no matter what the algorithm is, you can always find a logging policy and a target policy such that the logging policy still guarantees you the uniform feature coverage, but you can't avoid the target policy. So that's going to be the result, basically. But how to do that?
First, we should, I guess, change the S0 somehow, just not to continue in the same way for all the policies.
Right. So somehow, when you're exiting, if you stay there and you will get all that beautiful samples, then it will be just too much, right? Like too much information. Then you immediately see what the value of kappa is, and then you can avoid any policy. So yeah, like you have to modify the dynamics. You make it stochastic so that it doesn't tend to stay. So you don't tend to see the value of kappa. You tend to be thrown back, and then it will be really hard to get to the line where the information is.
Just build a giant tree.
I think that you just modify this dynamics in such a way that that here you would be exiting right after you jump out with very high probability, and then you just have to show that things are still consistent and the values depend on the value, like sensitivity to kappa is still there, and you can make it work. Anyway, so if you do that, then the result of that is going to be this theorem. So it's pretty much the same, except that QH kappa has stochastic dynamics, stochastic rewards. Otherwise, everything is the same, and the statement is going to be that there exists a logging policy and the target policy such that for all A, epsilon data sound, the number of samples this algorithm needs on this MDP with the features and epsilon and data and the logging policy and the target policy and S naught and whatever is going to be I think it's like minor difference. While the logging policy is not arbitrarily bad, it's a good policy in the sense that if we take the induced distribution over the state action space by the logging policy, then the minimum eigenvalue of the corresponding design matrix is still, hold on, in fact it's like just in there. So the logging policy will mostly stay in. It will not give you the information about the reward or the kappa. That's how you do it. All right, that's all. All the bad news. So next time, maybe we get some better news. I don't know. Yes.
In theorem 1, where did you use that the size of action space is true? Because it looks like it's true for any size and any action space of any size.
Yeah, sure. I mean, like, if you can prove it for, like, it's even stronger if you say that it already holds for 2 actions.
Yeah.
So yes.
It holds true for action space of any size, right?
Yeah, yeah. Except for 1. If there is only 1 action, so here there's only 1 action, so maybe that's not a stupid question to ask. Maybe the hardness result is still there for the finite horizon case. Is it? Maybe it is there. With that construction, it's not. Yes.
If we require like above this, like besides this assumptions, we require that the logging policy or state occupancy of logging policy has some closeness to our state occupancy of the target policy. Can we get rid of these
Sure.
problems?
Yeah.
This is too much to ask, or is it okay?
I don't know.
Most of them, like the logging policy is
Right.
to doing somewhere that.
So, of
target
course,
market is like-
we want to be ambitious. We don't want to ask for this. We are trying to see whether we can get away without asking for this. This would obviously solve the problem, because if they are the same, then like there is no problem. We just had the data that we wanted to have. That's awesome. And we also know that little gaps can be tolerated. That's pretty easy to see. Question here is whether you can push it further.
And one other thing, like if the target policy and the like logging policy itself are somehow close, does it guarantee that the state occupancy is going to be like close to or not?
There is continuity in some sense of you can write the occupancy measure as a function of the distribution over the actions of the policy. So it's like there is some sort of continuity happening. Less so, I think, in the finite horizon case than, for example, if you have some recurrent structure with some mixing, then there would definitely be continuity.
Somehow like maybe like important sampling stuff, like when the probability of those important sampling ratios is not very low. Like,
Yeah,
it's
something like
completely.
that. Yeah, but these are patches, right? Like it's like we couldn't come up with anything better. There are these very simple ideas, and then people are, like they also bring in fancier stuff of like reweighting and distributionally robust optimization, and then let's bring in, I don't know, Wasserstein measures and all of this, and then yeah, you can do it. I'm not sure where it goes, and this could be interesting if you could see some real differences between us. Sometimes maybe you can, but like it's a little bit, yeah, it's not so clear where it goes when you're doing this. And this is more like the other side of asking the honest question of like, but like, do we need this? Do we need bounded, I don't know, importance weights? And the answer seems to be, yeah, mostly. I mean, like, at least on that condition, you can get something. But if you're looking at examples like this, then maybe it also crashes optimism that, like, okay, maybe that's a little bit too much to ask. But if you ask me, like, is it too much to ask for? No, I mean, like, what you have is what you have. Like, when you're working with some data, it is not going to, like, if it's the best setting, then you didn't have control over it, or you should think ahead of time, and then maybe you should be on an online setting, and then control it. So I think that all of what this is teaching us is that, yeah, like, maybe epsilon small improvements are possible if you're in a bad setting, but one shouldn't really expect miracles. In many ways, this dream that you just like have little snippets and then you're gonna paste them together into trajectories, and then now you can, like emulate and simulate and like everything's gonna work. It's gonna work in very special cases. And it's kind of like, okay, this is just like asking, yeah, like how special, and try to go from the other, like, yeah, so in my mind, very often, maybe I already drew some picture like this. Looks like this is all the problems we want to solve, it's a big bag, and then we're cutting off, like, this is impossible, this is also impossible, this is also impossible, and then some people are working here and they say, oh, this is possible, this is also possible, and then someone unifies, this big thing is possible. So you can do these two different activities. Either you go from inside and you go from outside. At the end of the day, you want to understand how all of this works, right? Like, if you have full coverage and like multitudes of understanding. It's not just like one understanding, because like depending on, like this was the other picture, like depending on how you slice it, you will see different effects. So yeah, I don't know. Maybe I'm just drawn to these negative results because I think I like them because
You don't like batch RL?
I don't know. I mean, like, so when I moved to Alberta, I was first working on batch RL for, I don't know, 5 years.
Oh, really?
Yes, it was, yes, and it was work. It's like, because you get all these conditions, so you feel more like work because you get all these conditions under which you can get positive results, and then you ought to ask whether those conditions are really needed or not, right? And a lot of people are questioning what you do because you come up with this condition that, oh, the importance weighting, like this measure of that measure, like should be nicely behaved, and like why, like do you really, and no, but without it you can't. So it's like maybe flipping completely to the other side, like once you exhausted yourself a little bit on trying to come up with constructive things, then you say that, well, okay, now I need to see whether what I was doing did make sense in terms of like, can I remove any of these conditions? And then, okay, now it appears that you can't, so nice. Yeah. Okay, do we have questions on Slack?
Nope.
Okay, because we don't have any lecture notes. I don't know what to do about that, but I mean, like, I should write the lecture notes, but besides that, the fact that we don't have questions, like, okay, you can watch the
Yeah, there's videos.
lecture from last year, and then you can look at the slides. Just looking at the slides, you could have questions, right? Like, this doesn't make any sense. Like, well, what did you write on this, or the whiteboard saying?
Maybe what we can do is for all the lectures, put the corresponding papers that might have inspired said lectures, so at least you can, well, like, there's one lecture that's just UCRL, so you can just be like,
Yeah.
if you want to come up with a question, feel free to read that paper. You can ask a question at least about the paper.
Right.
Or
Yeah.
this lecture, read Phil's counterexample and
Right,
the
right.
one.
Yeah. Eventually, I will write these, but for now,
They're
it's
negative
ISIMA
anyways.
time.
They're negative anyways, it's okay.
Yeah. It's like, who wants to remember this? It's like, just want to forget it. Yeah.
Have we done the exponential overlap yet?
Which explanation?
Johnston and the shot. Oh, we did that earlier.
Yeah,
Yeah, forgot when we did that.
it was happening
In planning.
a long time ago.
We had
I think was that originally a batch RL result? That exponential? But the original one where they used that lemma,
No, online,
that was an on.
because it makes it stronger.
I just remember
It's
that paper.
online. It's like
Online.
epsilon optimality with approximate reliability in this
Right.
planning setting. Yeah. No. So this is a paper that comes after, and at the time people were all thinking about, oh, this GLMI is all that you need, but no, it's like in the batch setting, no, none of this is needed. You just don't get information.
I have a general question of something I noticed. So like, a lot of these results are actually very recent that we've seen, especially
Yeah.
like with function approximation for planning for this batch stuff is like, I feel like the oldest ones I see are like 2018 or 2017 or something. So what was going on before? Was everything just, was there like?
So as I said, I was, for example, working on upper bounds for the same setting, and then churning out one result after the other that had these very, very obscure conditions in them. And a lot of other people were doing similar things. We were pretty convinced that you can't remove those conditions. We were a bit lazy to actually show it. And And so that was what's going on, I think, that some people started to, like, we got the critical mass so that people got interested in lower bounds. And like, you can write lower bounds, but if no one cares about it, like, it's not good. So if you have the critical mass, then it becomes much easier. So I think that's why you see this explosion of the number of articles on this topic, is because we have a much more active theory community now. Like the whole field grew, with it, the theory part of it grew as well. And I think that people are just like more active because it is more fun.
Yeah. So, but before there was results, I guess, in like, for instance, like in planning a function approximation, they just were worse. They weren't as strong as the ones we have now for the different settings.
I think people also cleaned up the notation and the problem statement. Like if you read some of the earlier papers,
Yeah.
even I'll read them and just be like, I don't exactly know what they're asking. Not in a bad way, but the analysis also got better, I think. Less
Yeah.
contraction arguments, you had some of these nice like statistical concentration arguments.
Yeah, I don't know whether. Yeah. So earlier the contraction arguments were really dominating, and you get rid of them when you're proving lower bounds, of course, because the lower bound shouldn't care about like what technique you're using.
Yeah, there were the nice string of papers. There was the Azar paper that had some nice analysis. UCBVI. There was Chijin did some work with some good.
Well, there's been
Yeah.
lots of papers.
Oh, I meant in terms of like at least what the recent papers kind of what like formalisms or like what papers they seem to be borrowing a lot of the arguments from.
Right.
Oh, your paper with Yasin as well.
Which one?
Stochastic linear bandits.
But that's bandit paper.
Yeah, but that made that elliptical potential lemma like just appears in a lot. Like it's like one of those like auxiliary lemmas in a lot of
We
papers.
stole it. Well, we were citing the source, so I don't know why people are citing us. So you just write the paper better, and then
Yeah.
I think that's what's happening. But no, it's like, I think that 15 years ago there were maybe 10 people who cared about theory in RL at all. So imagine that.
Now it's like
That like my average class would have 3 students most.
Take a long time to fill in the table then.
Yeah. And then you do whatever you do, but like at your own leisurely pace, and you get to somewhere. Of course, you could have done much more, but someone's gonna do it anyway. So it's like, what's the rush?
also wasn't
So good.
the bandit literature also wasn't there yet.
The bandit literature was evolving a little bit earlier, since the, I don't know, 95s and something like that, maybe 2000s.
But I meant like based on the bandit course, it seemed like there was a lot of activity between 2005 2016. Like in terms of like a lot of
so
nice, strong.
yeah, exactly. So that's also kind of natural.
I feel like our theory would have came after people maybe slowed down in the bandit literature and then maybe started asking the
Exactly.
fundamental
So what makes RL special? So one aspect of RL is that you're actually interacting with the word. You have to think about how to collect data to get better. So that's the explore-exploit question. And you can start to study it in RL, but that's complicated, so you rather simplify it first. So when people were interested in RL, like you naturally simplify it to bandits. Once you are kind of understanding a little bit about what's happening there, then maybe you can move on to RL.
Yeah, and then like I guess for bandits to have started, Gabor and Miklo had to write that online learning book because you need those tools to understand. Just how do you even what do you do with like
I mean,
online regression?
that is yet another interesting
Yeah.
story, because their angle was absolutely not that. It was not exploit.
Yeah.
It just happens to be like one special case for them. Not maybe the most interesting idea, but they were really interested in this instance-based formulation of machine learning, I would say, where you're not necessarily worst case, or maybe you're a little bit more worst case, and then you get rid of the statistical assumptions. You want to understand what statistics buys you by not starting with statistics. If you remove it, then you can ask the question like, can I get the same results with some other tools, or like similarly powerful results? So that they were basically asking that question, that it has an overlap. It's like, okay, that's the miracles of math, right? That everything depends on everything else.
Well, yeah, I guess maybe what I meant is like, when that book was written, it just seemed like all these like EXP3 type algorithms started getting studied, and I think people had more tools to look at the bandit problems, and now you see these like mirror descent, optimism.
Right.
And then even now in RL, it seems like, I guess what Dylan has been doing, reducing these bandit RL problems to these online regression problems, so you can just use the tools from that book.
I mean, that's been an ongoing project for Dylan and others, to reduce anything to just supervised learning.
Yeah. Yeah, because we were reading the Philgood-Thompson sampling paper, and I think his big insight is like you can reduce these bandit problems to just these type of like old style mirror descent problems. I don't know how useful it is. I guess you needed all those tools to get to where we are.
Yeah, sure. Without those tools, you wouldn't have these papers. All right. Stop here.